Okay, so now that we know a little bit about vectors, we can start looking at the actual transformations. Translations are really easy. Okay, if you think about translating by a vector or its position vector, even the change in y and the change of x, if that's just hk, if we're looking at a position vector OP that's going from the origin 0, 0 to p, which is at hk, then the notation for our translation was the translation t sub op from o to p of a is a prime. Well, if a is xy, we can say a prime is x prime y prime. That's a common notation in our book. You just add the change in x to the x coordinate and the change in y to the y coordinate. Okay, so if your position vector is hk, to translate a point in the plane by that, you just add h to the x coordinate, y to the k coordinate. Again, let's look back. This is actually the same construction as my position. It's actually why it has these actual labels, so I can change hk in this picture. But to translate a by that vector, I just have to add h to the x coordinate, k to the y coordinate. Okay, so translations are the simplest by far in terms of the coordinates. Whatever the translation vector is, you just add the x amount to the x coordinate, the y amount to the y coordinate, and that's it. Okay. For the video, I'm not going to do a lot of the numerical examples. You can look in the book. There are numerical examples of these. I will point out, though, if you are doing the translation, and again, O is always going to be the origin, so that's not listed. But if you do from O to P versus P to O, that's in the opposite direction. You need to reverse, change the signs on H and K when you go in the opposite direction. Okay. Let's look at rotations next. This may look familiar if you've had linear algebra and you've done this with matrices. Let's see where this comes from. A rotation about the origin at first. Okay. So theorem 5.4.3 says if A is equal to xy, and it's any point in the plane, and we're going to do a rotation about the origin, that's a little o, about the origin by theta degrees, which by convention is going to be positive, is going to be in the counterclockwise direction. Then A is going to go to A prime, which is going to be x prime y prime. It's going to have coordinates. The x coordinate turns out to be x cosine theta minus y sine theta, and the y coordinate, y prime, turns out to be x sine theta plus y cosine theta. Okay, I have a fairly involved GeoGebra construction to walk us through the proof of that, and it's really pretty simple. It's a really neat application of the addition and subtraction formulas for sine and cosine. And I can, in this picture, I can change the angle. I didn't change A, but I can change the angle of rotation. I can actually move A as well. But here it is written in matrix form. Okay, if you know how to do the matrix multiplication, right? If I were to do this, I would do this row times the column. I would get x cosine theta minus y sine theta would be equal to x prime. X times sine theta plus y times cosine theta would be equal to y prime. So there's the translation matrix to do this in terms of rotations if you're familiar with linear algebra. But if not, we just have formulas for x prime and y prime. Okay. So first of all, I've got a point in the plane, A, which has coordinates x, y, just an arbitrary point. For simplicity, I've put it here in quadrant 1, but it would work in other quadrants. This line, or the ray, from the origin through A, has angle of inclination alpha. And then we're going to rotate from that by theta to find the point A prime, so the distance will be the same. The origin to A is the same from the origin to A prime because we're rotating about the origin. And the angle between those two is going to be theta. Okay? We can use trigonometry on these. Here's the trig coordinates for A. Okay? I claim that x is r cosine theta and y is r sine theta. Okay? Where r is for the radius of the circle if I'm rotating it around from 0 out to the point. R is the hypotenuse of this triangle. X is the x coordinate of A, which would be this side of the triangle, and y, the y coordinate of A, would be this side of the triangle. If you look at that triangle, and we just do the sine of alpha would be y over r, opposite over hypotenuse. So if we rework that, y is going to be r sine theta. So y is r sine theta. Similarly, cosine is adjacent over hypotenuse. The cosine of alpha is x over r, or it comes out to be x is r cosine theta if we multiply. Okay? So that point, A, has coordinates r cosine theta and r sine, alpha, whatever we call this angle. I may have been saying that wrong the whole time here. Alpha is that angle. So x is r cosine whatever the angle is for A, and then y is r sine whatever the angle is for A. Okay. We can do the same thing on A prime, and if we think about this, the angle of inclination for the triangle for that's actually going to be theta plus alpha. Okay. So x prime has coordinates. If we look at that triangle, this is x prime, this is y prime, the x and y coordinates for that point. R is still the same. The angle in the triangle is actually the sum of these two angles, alpha plus theta. So x prime is r cosine alpha plus theta, and y prime is r sine alpha plus theta. Okay. Then all we have to do is apply the addition formulas, do a little bit of trigonometry. We can come up with our nicer formulas here. So let's look at x prime. Here's my derivation. Okay. So x prime, we've said, is r cosine alpha plus theta. Well, you may or may not remember it. We have a formula for addition of cosine. If you go back and look at it, it's cosine cosine minus sine sine. So we have r times the whole thing in parentheses there. Cosine of alpha plus theta breaks into cosine alpha cosine theta minus sine alpha sine theta. Then we can distribute the r and kind of regroup it and think about what we have here. We have r cosine alpha times cosine theta in the first piece, minus an r sine alpha sine theta in the next piece. And then if we look back, we can do a substitution. R cosine alpha is actually x. R sine alpha is actually y coming from this point. Okay. If we plug that in, we get that x prime is just x cosine theta minus y sine theta, which is our result. We can do the same thing over here with y, and we work it out. This time, sine's addition formula, we get cosine alpha sine theta plus sine alpha cosine theta. Again, distribute the r and group it up, and again we have the x and the y with our r cosine theta and r sine theta. So it winds up y prime is x sine theta plus y cosine theta. So that's the formula for doing a rotation about the origin. If you know x and y and you know the angle, you can compute these things. Okay? X prime is going to be the x coordinate times cosine of theta, whatever that angle is that you're doing the rotation by, minus the y coordinate of A times sine of theta. Y prime is x sine theta plus y cosine theta. Okay, on this video, let's look at one more thing. Let's do a rotation that is not about the origin. How do we do that if our point's out here somewhere else? Okay, it's actually a pretty simple idea. We can just do a composition of things that we've already done. So let's say we want to rotate by some angle, and I've made a slider here so that I can move it if I want to, but I want to rotate by theta around point P instead of around the origin. Well, what I can do, and we'll do a composition of functions to come up with the formula, but I can translate everything to the origin. So P and the points I'm trying to rotate. I'm focusing specifically, I'll show the whole triangle, but on this point here, which has coordinates x, y, I called it x. So we would translate everything, so P is going to go to the origin, and then everything's going to translate by that vector, which took P to the origin, which would just be, if P is HK, since we're going from P toward A, we would subtract, toward the origin, we would subtract H and subtract K. Okay? So there's this vector, this point's translated by the vector, this point, this point. So this point goes from xy to x minus h, y minus k. So the translation to the origin is pretty simple. We just subtract off the position vector for P. Then we can apply our previous theorem and rotate around the origin. So I've rotated by theta. Let's go in. I'll just show you real quick. If I pick a point, let's say we pick the one we're looking at, and I go from there to the origin to there, that angle is the 55 degrees. And of course I can change my, if I get the pointer tool, rotate by different amounts. Okay. So our coordinates are from our previous theorem. The only trick here is our x and y are now actually x minus h and y minus k because we've already translated to the origin. So it's our x coordinate of the point right here, which is x minus h, times cosine theta minus the y coordinate of that point, y minus k times sine theta. Then the x coordinate of that point times sine theta plus the y coordinate of that point times cosine theta. So it starts getting a little more complicated because we're doing a composition of functions. But we translated down, and we're going to get a single formula that does this in one step, but this is the proof or the derivation of it. We would translate everything toward the origin by this vector P to the origin. So we just subtract off the h and the k. Then we plug that for x and y into our rotation formula, and then we just translate back. Okay, we pulled everything to the origin, we need to send it back. So there now, let me rotate this thing. There's actually the rotation around the point P of our original triangle. Okay. And when we translated it back, what did we have to add to the formula? Not much. We just had to add hk to the x and the y. So we took our formula, which had the trig in it here, and I added h to the x coordinate. And I took my formula, which had trig in it, and added k to the y coordinate. So that's actually the final result. We have a single formula. It gets kind of long, and I'm going to allow you to have a little note card and write all these formulas. You just need to be able to apply them. But there was the full derivation. If we first subtract h and k, we wind up with these coordinates. We plug those in to the rotation formula about the origin, and then to the x and the y, we add h and k to send it back. Okay? So to do a single rotation about the point hk, I do x minus h times cosine theta minus y minus k times sine theta plus h. It's where we've translated it and then sent it back. And then x minus h sine theta plus y minus k cosine theta plus k. And there you go. There are rotations about any point in the plane.